Hi, Mike Mays here. Today I want to talk about a topic that weaves together several things that we've done in some of these earlier videos and some things that come later in this book, Math Hacks for Scratch. In particular, we talked about how you could calculate powers of a number various ways in Scratch. And I want to show you another way of doing that that has applications to something that we need later in the book. In the chapter about cryptography, we're talking about modular inverses. And it turns out that this technique for calculating exponents is a terrific tool for calculating modular inverses. So let me get started with this. Let's go to a Scratch screen and see what we can find to get into. First thing I'm going to do is to think about a topic from chapter 1, which was different ways of representing a number. One way was to write a number in binary, to write it as base 2. And there was an algorithm in chapter 1 that did that. It is successive divisions that will give you what the binary digits or the bits are that correspond with a given integer. So let's reproduce that. I'm going to do it this time as just a custom block because that'll be an easier way to use it. So I'm going to make a block to start, and the block that I'll make, I'll name toBinary. Just to remind myself that I'm going to use this to convert a number from decimal notation, regular notation, to binary notation, and I will put in that block an input for a number to convert. I'll call it n. So here is a block that will do that. We just have to remember what the code is going to be for it. I'll define a variable. I'll name my variable bits. That could be binary digits, and that's a good thing to keep track of. So I'm going to set bits to get started. Set bits to, and I want to put a blank here because what I'm going to end up with is a string of digits, but I don't want to think about it as a number. If Scratch sees a string of ones and zeros and thinks that's a number, it's going to interpret the number base 10. I'm going to interpret the number instead as a number that's in binary, and I'm happier to think about that as a string. So I'm going to start off with a string and have it be that. The argument that this custom block uses is n. I'd like to work with that, so I'm going to make a variable to shadow that, n for my variable, and I'll set n to that argument that I'm building from the custom block. And what I'm going to do is to work my way down. I'm going to think about n as being a number, and I'm going to change n as I generate more binary digits of the number. So for a control, we can repeat this thing until, we'll do our loop, repeat until n equals 0. And as I whittle through binary digits, I'll be making it smaller and smaller until I'll get there eventually. I want to do it until the variable n is 0. And what I'm going to repeat is this process. I'm going to add another binary digit to my bits string. So set bits to, now this is a string operator, so it's going to be join. And I'm going to join n mod 2 in mod 2, that's going to be a 1 or a 0, and that's going to be the next digit, so it's going to make bits that much bigger. Join n mod 2 to bits, and then I'm going to lower n to the next value down, I'm going to set n to floor of n over 2. So that's where I've divided through by 2. To get the next step down. And so I divide through long enough, I'm going to get to a value that is 0, and that's when the loop stops. And that's all it takes. That's the implementation of the algorithm. Now let's see, I've got bits here. I don't really need. Well, it doesn't hurt. So let's try this thing out. So here is, let's put the block up here and just play with it a little bit. Again, I don't really need to write a program to have Scratch Cat say things and ask for input and stuff. I can just work directly from this screen. It's like a debugging thing, really. But if I want to do 2 binary, say I want to convert 5 to base 2, well, 5 base 2 would be 1 plus 4, powers of 2, so 1, 1, 0 2s, and 1 4. 1 0 1 should be what comes out. So when n is, so the bits is 1 0 1. It shows the last value of n, that's 0. I don't really need to see that anymore. I'll just let that go. So 2 binary, 5. Let's do a fancier one. How about 15? 15 is 1 plus 2 plus 4 plus 8. So 2 binary of 15 would be 1 1 1 1. 2 binary, let's take a bigger number, 71, just to put something in, and out comes 1 0 0 0 1 1 1. Now what does that mean? You could think about that as 1 plus 2 plus 4, no 8s, no 16s, no 32s, 164. 64 plus 4 is 68, plus 2 is 70, plus 1 is 71. So 1 0 0 1 1 1 is 71 in binary. So that's a tool that's going to be useful for me. And now I said that this is something that I could use to keep track of calculating powers. And here's the trick. If I'm going to calculate powers, I can think about the binary expansion of what the exponent is as giving me a recipe for calculating what the power should be quickly. So here's an example. Suppose I wanted to calculate 3 to the power 71. Well, we just saw that 71 is a binary expansion 1 0 0 1 1 1. Now think about what that means in terms of what's happening here. This is 3 to the power 1 0 0 0 0 0, so 3 to the power 64. No 3 to the power 32nds, no 3 to the power 16ths, no 8s. 3 to the power 4 is what this one signifies, 3 to the power 2, and 3 to the power 1. So these binary, the digits that are not 0 in the binary expansion tell me powers of 3 that I should multiply together to give me 3 to the power 71. And here's the trick, 3, and then I could just square 3 to get 3 squared, and then I could square 3 squared to get 3 to the 4th power. I'll square again, 3 to the 8th, square again, 16, square again, 32nd, square again, 3 to the 64th power. So successive squarings will give me the right value to use for this 3 to the power 64. Now, I made the point, talking about doing arithmetic in Scratch, that it is set up to give you exact values. The actual true number that comes out is going to be true up to a number I called Flint Max. That was 2 to the power 53. It's a big number, but it's only about 17 decimal digits. So if you want to work with numbers bigger than 17 decimal digits, Scratch will keep track of them approximately, but it won't keep all the digits. It'll be kind of rounded off. And what that means is that if you want to do things in number theory where you really need to know the exact value of the number, you get to the point where Scratch gets confused. Now here's a trick around that for doing not regular arithmetic, but doing modular arithmetic. Every time a number gets too big in modular arithmetic, every time it gets bigger than what you've set as the modulus, then it starts over again. So you don't get this overflow issue that comes up. So what I'm going to do is to do a process to calculate powers, but I won't do the power of the actual number, but I'll do the power relative to a modulus. So I'll do a modular power, and that's going to turn out to be something that's a very useful thing to have. So let's think about what I need to do. Again, I'm going to set it up as a custom block, and my new block is going to be what I will call mod pow. So a power mod, a power relative to a particular modulus. And for the input, I will put what I want to raise to the power, so I'll call that base. And I'll add an input for what I want the power that I'm raising it to, the exponent. And I'll also put in something to be what the modulus is. So this is a new custom block, and now I get to define it. So mod pow. Let's see what's going to happen here. So the base value, I'll start by setting mod pow. I want to introduce a variable to keep track of. I'll call it the output of this custom block, so I'll keep mod pow, not only the name of the block, but what the output will be, the thing that I'm going to calculate, and the start thing will be to set that equal to 1. So if mod pow is equal to 1, and now I'm going to keep track of successive squarings to incorporate into the value that I calculate. So I'm going to need a variable multiplier. I can call it that. If you're following along and you want to call it something else, you certainly can. But I'll set now my multiplier equal to the thing that I'm starting with. That would be the base. So that's 3 to a power in my example. So the base is what would come out there. The first step is going to be to call that to binary, and I'll have a number when I call it to binary. That's going to be for the exponent, and then that's going to give me the variable bits that are the binary digits of what I have for the exponent. So now bits is a variable that the program knows about. So I'm going to work my way through the string of bits one at a time. So I'll put in a variable I to be like a counter for the bits that I have. Start with then set I equal to length of bits. So that's how many binary digits that I'm working with. And now I'm going to go just step my way through. I'm going to step my way through the binary digits of the exponent by this trick of successively squaring. And if I've got a binary digit of 1, I'll incorporate the value of that square into my multiplier, or into what I want the answer to be. And if it's 0, I'll just step to the next one. So here goes. Repeat length of bits. So here's the trick. If, so under control, I'll need an if. If the particular binary digit is 1, then I want to use the right multiplier to change what I want the reported answer to be. And otherwise, I want to ignore it. So if letter I of bits is equal to 1, that means I've got a binary digit of 1 there. Then I want to change the value for what I'm going to report for mod pal. So set mod pal equal to mod pal changed by, so multiplied by mod pal times the multiplier and here's the trick. This is done not as an absolute number, but relative to the modulus. So it's mod pal times multiplier mod the modulus. So here's a place where if the numbers, I'm doing all this squaring and multiplying stuff together, if it gets too big, it's going to get to the place where I don't have exact arithmetic anymore. But doing it relative to this modulus, the numbers never get bigger than roughly the size of the modulus, just maybe a little bit bigger than the modulus, but not to the place where overflow is an issue. So then I've changed the value that I'm going to report out mod pal in that case. Otherwise, I'm going to go through and update the multiplier. So that goes here, set multiplier to same kind of a deal. It's multiplier times multiplier. Just square it. That's where I've squared it. The modulus. And now I'm going to step to the next bit in my exponent. And since I started at the end, at the far end, I started with I being the length of the bits, I'm working my way backwards. And that kind of is the way you write down a number in binary. You write the least significant digit to the right. So I'm stepping backwards, so I have to change I by -1. And this is all. So this is all there is to it. Now we can check and see what comes out here. Let's see what we need. I don't care. Bits is nice to see. Mod pal, that's the number I really want. Multiplier, I don't care if I see along the way. And I don't care if I see along the way. So mod pal is the only thing that I really care about. Let's try this out. Let's do mod pal of, say we do a value of, well, let's do one just to make sure it's doing exponents right. 2 cubed is 8, right? So 2 to the power 3. And if you have a big modulus here, say 100, then it's just going to do the work. 2 cubed should be 8. And 3 came out. That's what the bits are for 3. So sure enough. How about 2 to the power 10 mod 100? Well, this thing you might remember, if you know your powers of 2, you might remember that 2 to the power 10 is 1024. So I expect the answer 1024 mod 100 is going to be 24. 24, and here's 100 in binary. Well, let's see, what is that? Here's 10 in binary. So 8, 9, 10. So there's the exponent, and there's what the modular power is. So I could calculate crazy values. I could calculate 3 to the power 1,000. That's Scratch would think that's infinite, but it doesn't. It knows 3 to the power 1,000 mod 100 is, it's happy to do that calculation, and what comes out is 1 for the answer. So whatever the number is, when you multiply it all out, 3 times 3 times 3 times 3, 1,000 times, mod 100 means that it ends in 0, 1. So a very powerful technique. Now here's what that's good for, and this is where I want to bring back that business about modular inverses. There's a famous theorem in number theory. It's called Fermat's little theorem. It says that if you take a prime number and you take any base at all, you raise the base to the prime power and you get back the number that you started with. A to the p is the same thing as a mod p. That works for any number. And if you think about this as an equation and you divide through by a, as long as a and p are relatively prime, then the equivalent equation is a to the power p minus 1 is congruent to 1 mod p. Now, you might not believe that. We could go back and kind of see that that's true, just to sort of try a few cases. Let's try 7 just as a base. And suppose we want to do this for the prime of 13. So 7 to the power 12, what is that mod 13? 7 to the 12th power mod 13 is what mod power calculates for me. Ha! Came out to be 1. 7 to the 13th power mod 13 is 7. 11 to the 13th power mod 13 is 11. So this is like an illustration of what that theorem says. Now here's the point of it. If you know that a to the power p minus 1 is congruent to 1 mod p, then you've got a times a to the power p minus 2 is also congruent to 1 mod p. This is just how the exponents work. You multiply by adding exponents. So the point is, if you start with a, then you calculate for a particular prime modulus p, you calculate a to the power p minus 2. That is a number which, when multiplied by a, gives 1. That is a modular inverse. So this is a calculation, a completely different way of calculating a modular inverse. If you dig out my book and read through it, there's 2 ways mentioned in there. One way is to just look at it till you find it. And the other way is to do a tricky unwinding of Euclid's algorithm to come up with a value for the modular inverse. So this is a completely different way. Fermat's little theorem and the little bit of code that we generated is all we need to calculate a modular inverse right off the bat. So let's go back and look at the Scratch screen and think about that. So with just this code and no more code, suppose the deal is you would like to know the modular inverse of you'd like the modular inverse of 9 mod 29. So 9 to the power, so 29 is the modulus. And so p minus 2, 9 to the power 27, mod 29 is 13. And now 9 times 13, (9 times 13) is 117, and 117 mod 29 is 1. So this is how a calculation could go. If you need a modular inverse, out it pops just by this process of calculating a power. And the power doesn't get overrun, doesn't have an overflow, because it's a modular power. It wraps around and you never get to the place where Scratch is approximating and giving you the wrong answer. Really pretty little bit of arithmetic tying together several things that are interesting math topics that Scratch can talk about, Scratch topics that math can illuminate. Goes both ways and fun to talk about. So this is it for today. Talk to you another time.